we are going to discuss photoelectric effect. The topic is marked as dual nature of radiation and matter. This is unit 7. Remember, we have only 9 units this year, right? Okay. Dual nature of radiation and matter. So we have seen light, and light and the various phenomena related to light were explained using that means very phenomena like interference, diffraction, polarization, etc., were explained using the wave nature of light. But every time, wave nature of light cannot be used for explaining further phenomena in light. That means advanced phenomena in light. For example, in the case of what you call photoelectric effect, that also connected with the radiation only. Without radiation, photoelectric effect cannot take place. So in that case, we cannot explain photoelectric effect if we take light is of which nature, wave nature. So in that case, radiations we have to consider radiations are not not exhibited or not traveling in the form of waves, but in the form of particles. So this must be the way of life in the modern times, that light sometimes behaves like waves and sometimes behave like particles. So we have to consider radiations just like light. I mean, visible radiations, X-rays, gamma rays, etc. They are waves in some extent. That means we have to, when we have to explain interference, diffraction, polarization, etc., we have to take radiant energy as of wave nature only. But the phenomena like what do you call this photoelectric effect. Photoelectric effect also electron emission, etc., cannot be explained taking light of having the nature wave, nature of wave. But in this case, we have to take light consists of particles. So light sometimes behave like particles and sometimes it behaves like the waves. That must be the concept we have to go on when we study this topic. So this is for the first time it was said by de Broglie, who put forward a theory that any particle that is moving with a certain velocity that is associated with a wave. That was a concept he given to us. That means any particle which is moving with a certain velocity is associated with a wave. After some years, a scientist called Davison and Germer proved it. Actually, the theory was given by de Broglie in 19, I think, in the year of 1924. In the year of 1924, de Broglie said this theory that particles or matter when moves with a certain velocity that is associated with a wave. And he named this wave as matter wave, or sometimes called as de Broglie wave. This theory was only a concept given by de Broglie. In the year of 1927, the thing was proved, that theory was proved experimentally by scientists called Davison and Germer. Two scientists called Davison and Germer. Davison, Davison, Davison and Germer, Germer. Davison and Germer experiment is there, but in this year it is excluded from the syllabus, right? Okay. They proved it experimentally in the laboratory. That is actually they took most moving with a very high speed that is associated with the wave, and also they have shown that electrons can be diffracted. Electrons cannot be diffracted, but waves can be diffracted. So they said that when electrons moving with a very high speed that is associated with a wave, that they could diffract. So diffraction phenomena was seen with the high speed electrons moving with very high speed. So this was the This was the experiment, de Broglie experiment, and the proof of that was done by Davison and Germer, right? So here we have to, today we have to discuss certain things related to photoelectric emission. What is photoelectric emission? Electron emission. You know, everybody that every metal, every conductor has large number of electrons in that. Electrons, from where these electrons are coming? Electrons are coming from the outermost orbit of every atom, right? So outermost orbit of electrons are not at least bound electrons, and certain situations these electrons can jump out of the outermost orbit. Such electrons are called free electrons. These free electrons, what they do? They move to and fro inside the metal. They cannot leave the surface of the metal because there is a surface barrier. Surface barrier means electrons have negative charge, and atoms that leaves electrons that has positive charge, that has proton, that has the charge of a proton. So when electrons are to try to jump out of the surface, there is a backward pull from the protons or the positive charges or the positive ions. So due to which electrons are not able to leave the surface of the metals that contains large number of electrons. And if it's large number of the electron density in a conductor is very, very high. But these electrons are confined to remain inside the metal only because there is a surface barrier. What is surface barrier? Surface barrier is the backward pull acting on an electron by the positive ions or protons, we can say, because when an electron is left from an atom, its one positive charge increases. One positive charge of an atom, that is what is called proton. So these protons or the positive charges pull these electrons backwards. Therefore, these electrons are not able to go out of the surface of the metal. So if we need to jump this, or if we need to liberate this electron from the surface, we have to give some extra energy. This energy required is called work function. That depends on the nature of the surface and also nature of the metal. And this is called work function. If we give extra energy, that is equal to work function of the metal. Work function of the metal is depending on the nature of the surface and also the nature of the metal in which the electrons are present. Then these electrons, using this extra energy, they jump out of the surface of the metal. They overcome the surface barrier and becomes free. They comes out. This is such electrons are called emitted electrons. This is called photoelectric emission, right? Different metals have different values of what is called work function. That is charted in the book. Different metals like cesium has 2.14, potassium has 2.34, 3, sodium has 2.75, calcium 3.20, molybdenum has 4.17, then lead has 4.25, aluminum 4.28, mercury 4.49, copper 4.65, silver 4.70, nickel 5.15, and platinum 5.65, etc. That is charted. So these values are different. And also you will see that even cesium is CS, cesium, potassium, sodium, calcium, etc. has the least value of work function. So those metals, alkali metals like sodium, potassium, calcium, etc., can emit electron, even visible radiations to fall on them, right? While zinc, cadmium, and magnesium, etc., also can show the photoelectric effect or photoelectric emission or electron emission when radiant energy falls on it. So radiant energy, remember that radiant energy is not of, for this topic, you will remember that this radiant energy or the radiations or light radiations, visible radiations, UV radiations falling on a metal surface so that electrons are emitted out of it. This process is called electron emission. In this case, this radiant energy, they have they have only particle nature of light. So we don't consider they are having wave nature of light. So if you consider this radiant energy are having wave nature of light, we cannot explain a photoelectric effect. So time being, we had to consider the radiant energy, light, that means visible radiations, and what is called UV, ultraviolet radiations, infrared radiations, etc. They are having a particle nature of light. Particle nature of light means these radiations are consisting of small particles called photons. Photons are also called as quanta because they have a quantity of energy associated with that. This energy, this quanta or photons, when falls on the surface of a metal, the energy is transferred to electrons, and electrons are now easily able to come out of the surface of that metal. And or we can say that they can overcome the surface barrier of that metal. And this energy supplied by the radiant energy in terms of photons is called a work function of the metal. That means the energy of the photon when equal to the work function of the metal, then electrons after absorbing this energy are able to come out of the metal surface. Right? This is called a photoelectrons. Such electrons are called what? Photoelectrons. And also, you must remember that alkali metals can show photoelectric effect, even what you call visible radiations falls on it, right? So this is called this is explained into two figures are shown here. One is this figure. That means this has two metals. One is called anode. This one is anode. That I have marked it anode, and this is called cathode. Cathode is denoted by C, and anode is denoted by A. Anode is why it is called anode because this is connected to positive of a battery, and this is cathode is connected to negative of a battery. So this is having a negative potential. Cathode is having a negative potential with respect to anode because anode is having a positive potential. So far, when light is not falling on the cathode is the light sensitive material. It is a metal that is light sensitive. Light sensitive means when radiations of certain frequency, when falls on it, that can emit electrons and can exhibit the phenomenon of photo emission. So that is what is called cathode. So far, when light is not falling on that, this micro emitter does not deflect. When light a certain frequency and above that, that means that the minimum frequency at which a metal surface can emit electrons out of its surface is called threshold frequency. Is called threshold frequency. So threshold frequency is a frequency that is a minimum value of frequency required for a metal surface so that it can emit electrons. That will just emit electrons, that's all. Those electrons doesn't have much kinetic energy, but that frequency is sufficient for the metal surface to bring out electrons out of the surface. That frequency is called a threshold frequency. When in this case, the radiations of a frequency which is just greater than or equal to threshold frequency, electrons are emitted. So if the frequency is greater than threshold frequency, they will have kinetic energy and will move towards the anode. And the space between this cathode and anode now becomes completely filled with the charged particles and conducting. And so the circuit becomes closed and an electric current starts flowing in the circuit. This electric current is called photoelectric current or photo current. Understand? So this is the actual thing. So before before in the radiations are incident on this cathode material, no current will be flowing in the circuit. Why? Because the space between the cathode and anode is highly insulating. It is vacuum we can create. This is a vacuum glass bulb, so there is nothing is there, and no particles there. Therefore, the between these two plates, high insulation was kept first. Then after that, what you do? You will incident radiations of a suitable frequency. That frequency, if it is greater than threshold frequency, electrons will have kinetic energy also, and they'll move toward the anode. And the space between anode and the cathode becomes completely filled with the charge of the particle and hence conducting. So the circuit becomes closed and a current starts flowing, and this phenomenon is called a photoelectric effect. Am I correct? And the current so produced is called photoelectric current. So there are so many experiments related to this one that can be explained by this experiment. This experiment is called Leonard's experiment. In Leonard's experiment, it is very clear that there is a glass bulb is there with a window. This window means there is a filter is there. That filter is quartz filter. Using that filter, the intensity of light can be changed. Intensity of light can be changed using filters of different colors, right? Okay. And there is a cathode here. There is an anode here. The cathode, you see, cathode is kept at a negative potential. See, negative is connected to the cathode, and anode is connected to see. Anode is connected to the anode is connected to the what? The positive terminal of the cell. So anode is at the positive terminal and the cathode is at the negative terminal. We can say that the cathode is kept at negative potential with respect to the anode. Till when there is no radiation of suitable frequency falls on the cathode. One more thing you have to remember. Cathode is a light sensitive material, photosensitive material. Better you say photosensitive material. So on the photosensitive material, and also it is kept at a negative potential. So far, when radiations of suitable frequency falls on it, electrons are emitted. There are two things. One thing is that this radiations are radiation falling on the cathode material or cathode light sensitive material is getting extra energy, and also it is kept at a negative potential. So negative potential means that is there is also a repelling nature due to which the electrons come out of the cathode material and it will march towards the anode, and hence what is time an electric current starts flowing in the circuit. We can make a what is called a microammeter also here, micrometer, and this is the this voltmeter shows the accelerating potential applied with the anode with respect to the cathode. We can increase the positive potential of anode, we can decrease the positive potential anode, we can make it zero, or we can make it negative by this reversing key. This is a moving part. When this moving part is taken to this point, then what happens? This becomes more negative. When it is towards this part, this becomes more positive. So this sliding part, this moving part, this is what is called a rheostat as a potential divider. It is called rheostat as a potential divider. Using it, we can move it to and fro such that the potential of A can be made very high. Gradually, step by step, we can increase the positive potential of A. The potential of A can be made zero. The potential of A can be made negative also. If it is highly positive, all the electrons coming out of the cathode material are attracted by it, and the current goes on increasing. If it is made zero, then also some electrons are able to reach here because of the energy transferred by the radiation to the electrons. The electrons sometimes are having more kinetic energy because of the frequency of the radiation supplied, radiations made incident on the cathode. Electrons are getting more energy, so electrons can reach the anode even though the anode potential is zero also. That depends on the kinetic energy, right? Okay. And also, when the potential of anode can be made negative also, that is called retarding potential. That means potential is gradually step by step decreased such that the potential of A when becomes negative, then electrons are stopped coming to the anode, right? We can stop the current also, what is called photoelectric current. So such an arrangement, this is called as Leonard's experiment. So Leonard's experiment, using Leonard's experiment, what is the advantage of that? We can keep the potential of A positive. Step by step, we can increase the potential, that is called accelerating potential. Step by step, we can decrease that is the retarding potential. At times, if you need, we can keep the potential of A zero also. So this is the advantage of using this experiment. Using this experiment arrangement, we can explain photoelectric effect in certain steps. Number one is keeping the frequency of radiation a constant. frequency of radiation a constant, and the positive potential applied to the plate also fixed. That means the frequency constant and the potential applied is also fixed. The voltmeter will read only one value, right? And the frequency is also only single value. So frequency of radiation incident on the cathode material, cathode plate, and also the positive potential applied to the plate, both are kept constant. And the accelerating potential, if you go, sorry, but the intensity for going on increasing. Intensity, this is constant, and frequency also constant. What are constant? Frequency and the potential applied to the plate A, that is a positive value, is kept constant as it is there fixed, and also the frequency of radiation incident on the cathode both are kept constant. Then what you are doing, you are going to increase the intensity. Intensity can be increased by changing the position. That means the source of light is taken towards it or away from that, right? And frequency can be changed using different colored windows. Windows means the ports windows used, we can use of different colors and all, right? Thereby we can change the frequency of that. And the intensity can be increased by taking the source of light towards and away from that. Towards means intensity increases, away that intensity decreases. In this case, what you do, you are keeping the frequency constant and also potential given to the plate, anode plate also constant. What you are increasing, then you are increasing the intensity. It is seen that the photoelectric current goes on increasing proportionally. So that we can, that graph we can make here. That graph we can make here, right? There is this. That means keeping the frequency and the potential at the potential of anode plate, both are constant, and you are increasing the intensity of radiation. Then we can make a graph. This is intensity. Intensity is increasing, and this is what? This is photo current, I photo. I photo means photoelectric current. Okay, then it is seen that the photoelectric current goes on increasing, which are constant. The potential given to the anode plate and the frequency constant. If we increase the intensity of radiation, it is seen that intensity is directly proportional to current. Intensity is directly proportional to photoelectric current. Photo current. Because when intensity increases, the number of electrons emitted by the cathode increases. So photoelectric current in this case is increasing because when intensity increases, the number of photoelectrons coming out of the cathode material increases. When number of electrons increases, the photoelectric current is also increasing. This is the reason. The first experiment, we can use the same experimental arrangement. Keep the anode plate at a constant fixed value of potential, positive potential, and the radiation having a fixed value of frequency. But what we are doing, we are increasing the intensity of radiation. Intensity, how intensity can be changed, that also I have said that. This is the experiment number 1. The experiment, the graph is also done. From this experiment, you understood that intensity when increases, photoelectric current increases. The reason is that when intensity increases, the number of photoelectrons emitted by the cathode plate increases. As it is at the positive potential, all these electrons are attracted by that, and hence the charge flowing through in the circuit increases. Hence the current increases. That is registered by this microammeter, mu A it is called. This is not M, microammeter increases. This is experiment number 1. Next is experiment number 2. In experiment number 2, what is keeping the intensity and the frequency constant? If we increase the accelerating potential, again the condition is same only. The frequency and accelerating potential, keeping the intensity and frequency a constant. In this case, intensity and frequency both are constant, right? The last case, what we have seen that the intensity was changing, but in this case, intensity and frequency a constant. We are changing the accelerating potential, right? That's the condition. So then that also experimentally we can prove that this is a situation. A graph is made at different values of this accelerating potential. This is positive potential, and this is negative potential, right? What are constant in this case? Intensity is constant and also frequency is constant. Suppose that we are changing the potential of the anode plate from negative to positive. That means by changing this moving part of the uh, rheostat as a potential divider, we can apply first a negative potential to A, and that goes on increasing, right? Then negative potential increases means first it becomes a zero, then it becomes a positive. So from this point we can increase. So when you increase the potential applied to the anode plate from negative to positive, you will see that the current goes on increasing. The micro ammeter will show an increasing current, and it comes to that means at a particular voltage. At a particular voltage, it becomes the current becomes maximum and constant. On further increase of this accelerating potential given to the anode plate, there is no change in the current. So first it increases to a maximum. That maximum value is called a saturated current. Then on further increase of the accelerating potential, I will write accelerating potential. Why it is accelerating potential? Because it is changing from negative to positive. Negative first negative, then zero, then positive, increasing, positive, increasing, positive. So there is a graph like this you will get. This is very simple to understand. In this case, intensity is constant and also frequency is constant. Keeping the intensity and the frequency of the radiant energy a constant, if we go on increasing the potential, we see that first the current increases and comes to a maximum value, and then it becomes constant. On further increase of the accelerating potential, the change in current becomes equal to zero. That maximum current shown by the ammeter, constant maximum current shown by the ammeter is called saturation current. So it has come to the saturation level. There is no question of increasing that. If you want to increase the current again, we have to change the intensity. So this is intensity I, not the frequency. Now another intensity is used. Then you will see that. Then you will see that again the current goes increases to some extent again increases. Right. This is I2. So this experiment is done keeping the intensity I1 fixed. Frequency is same, right? Second case, the intensity is increased. The source is taken uh, still towards the cathode plate. Intensity, but remember the frequency is a constant. In both the experiments, intensity and frequency are constant. So in this case, I1 is the intensity and frequency is F4. In this case, the intensity is I2 and the frequency is F4, right? Okay. So like this it is. So intensity when increases, it is seen that the current is slightly increasing. Again comes to the saturation point. Saturation point means the number of electrons are coming out of the cathode plate becomes constant. That means there is no increase or decrease. That becomes constant. Therefore, current becomes maximum and saturated. Then, on further increase of the accelerating potential, there is no change in the photocurrent. So now this also saturated. If you still want to increase the current, then what you will do? You have to take a radiation whose intensity has to be increased. A third intensity use. A third intensity, this is I3. Then you will see that the current further increases. From this experiment, what you actually understand? That means intensity when increases, photocurrent increases. That is, photocurrent is directly proportional to intensity of radiations falling on the metal surface. Howsoever large the frequency is, but if the intensity is not changing, the photocurrent will not increase. This is the condition. So in this case, this experiment number 2 says that intensity of radiation falling on the cathode material, photosensitive cathode material, is directly proportional to the photoelectric current. Why it is increasing? Because when intensity of radiation falling on the photosensitive cathode plate, when increases, the number of photoelectrons emitted by the cathode plate increases. Hence, the photoelectric current also increases. This is an experiment. It's a very beautiful experiment, right? Suppose that the reverse condition, if you think that, suppose the accelerating potential is decreased, and when it comes to zero, the current is not becomes equal to zero. Current is this much, right? So this is a very interesting thing. Suppose that in this experiment, if you reverse the condition, that means the accelerating potential is decreased, and when the accelerating potential of the anode plate becomes equal to zero, then also the current is not zero. Why it is not zero? Because due to the kinetic energy of the electrons, some electrons are even at this condition also, some electrons are able to reach the plate and the circuit becomes completed. Understand? So when the potential of the anode plate becomes equal to zero, then also electric current is there. That means the photoelectric current is there. This explains that even when the positive potential applied, the potential applied to the anode plate becomes zero, then also some electrons are having sufficient kinetic energy to reach the anode plate. So from this section, what do you understand? From this experiment, we understand the fact that when the accelerating potential decreases, the photoelectric current goes on decreasing, but it is not becomes equal to zero. Decreases means the number of photoelectrons reaching the anode plate goes on decreasing, but it is not becomes equal to zero when the potential is equal to zero. Potential of what? Potential of the anode plate. It means the electrons emitted by the cathode plate due to the incident radiations, it is not a constant. Different electrons are having different values of kinetic energy. Here the kinetic energy is more, here the kinetic energy is less. Now, further what you do, you decrease the potential applied to the anode plate to negative. So suppose this is the negative value of potential plate, then also current is there, up to this much current is there. That means when a negative potential is applied to this value, then also some electrons are there whose kinetic energy is enough so that they can reach the anode plate. Again, suppose now impurity is further increased. What increased? Negative potential applied to the anode plate increased. Then also the current is not equal to zero. It means at this condition also, some electrons are having sufficient kinetic energy. So in that way, if you increase the negative potential to such a particular value, then all the electrons having even at a very high kinetic energy electrons are also not able to reach the plate, anode plate. Anode plate is actually anode plate now with very high negative potential is applied. Very high negative potential is applied means that negative potential is sufficient to stop all the negative electrons reaching to the plate. All the electrons are stopped. And this potential is called stopping potential. And this stopping potential is noted by D0. It is a negative potential applied in the anode plate. So anode plate when becomes negative and electrons also negative, and this negative potential is sufficiently enough to stop the electrons to reach the anode plate. So photoelectric current becomes equal to zero. Right? This is the condition. So in this case, this stopping potential, why it is able to stop the electrons? Because stopping potential, when a stopping potential applied to the anode plate, that does work. The work done by a potential is a voltage is equal to Q into V0. That means potential energy is equal to QV, right? That means the stopping potential works. The work done by the stopping potential is now enough such that it is equal to the kinetic energy of the electrons. Then the photoelectric current becomes equal to zero. So we can say a beautiful relation in this case. What is that? That is kinetic energy max, K max, Kmax is equal to EV0 we can write. What is EV0? That means the work done by the stopping potential is equal to the maximum kinetic energy of the electrons. Then the photoelectric current ceases to exist. That means no photoelectric current flows into circuit. So this is a very important relation. That is kinetic energy maximum kinetic energy of electron is equal to EV0. What is V0? This is the stopping potential, right? Sometimes it is also called as cutoff potential. Why it is cutoff potential? Because at that negative potential applied to the anode plate, no electron is practically able to reach the anode plate, and hence the photoelectric current becomes equal to zero. That potential is called stopping potential or cutoff potential. So maximum kinetic energy of electron is equal to EV0. What this relation tells you? Relation tells you that the work done by the stopping potential is equal to the maximum kinetic energy. Even electrons having very maximum kinetic energy also not able to reach the anode plate. That means current is cut off, and that potential is called cutoff potential or stopping potential. That's also understood, right? So this relation is very important. K max, or we can write it half mv max square. Half mv max, v square max is equal to EV0 we can write. K max is same as equal to half mv max square. What is m? M is the mass of an electron. What is v? V max is the maximum velocity attained by the electron. So this is another one. Next experiment is experiment number 3. Experiment number 3, what you do is that we are keeping the intensity a constant, but the frequency we time to time we are changing. Then what will happen to the condition? You will see that also. All these things. This is experimental arrangement. What is experimental arrangement? Is Leonard's experimental arrangement. So that I am drawing. So in this case, what we will use many frequencies. In a first experiment, the frequency is particular and intensity is same. In next experiment, we will take another frequency, but intensity is kept constant, and the accelerating potential is increased from negative to positive. Say for one particular frequency, what you see, if the experiment is done like this, this is I photon, and this is positive accelerating potential, and this is what is called negative potential. So this is zero. So one frequency we have taken, that frequency is F1, and the intensity is I only, right? We are keeping the potential of the anode will first negative, then gradually increases, becomes equal to zero, right? The photo current goes on increasing to a maximum value. Then after that, on increasing the accelerating potential, there is no change in the photoelectric current. This is a reverse condition. When the accelerating potential decreases, the photo current also decreases to a value. Even at the zero potential of the anode plate, also the current is not becomes equal to zero. If you apply a negative potential to anode plate, the photo current goes on decreasing and finally becomes equal to zero. And this is what is called stopping potential. For this frequency, we can take stopping potential is equal to V01, right? If you take another frequency, then you will see that the condition is different. So this is the situation we are getting. This frequency is F2. We remember that F2 must be greater than F1. In the same experiment, now we are taking a frequency F2 which is greater than F1. Then the condition is this one. So the reverse the condition only you will remember. So now you are doing an experiment with the intensity same. Intensity same means the source of light is kept at the fixed point. Intensity is same, but the frequency is changed. Frequency is changed means how it is changed? It is increased now. Increased from F1 to F2. F2 is greater than F1. Reverse the condition. That means accelerating potential in that particular frequency when used, you suppose that the acceleration potential decreased, then the photoelectric current decreases. Even at the zero potential also, the photo current is not equal to zero. We have to further apply negative potential to the anode plate. then what will happen? It is going on decreasing. What is going on increasing? Photo current is going on increasing. And at a particular value of stopping potential called V02, the current becomes equal to 0. Remember, V02, that negative retarding potential is greater than V01. Why this happened? Because in the second experiment, we have taken another frequency, that is F2 is greater than F1. From this experiment, it is clear that when frequency increases, the kinetic energy of electrons, the photoelectrons emitted by the cathode plate increases. That is why more work has to be done against that to stop it. That means the work done by the stopping potential must be more to stop the electrons coming out of the cathode plate when the frequency is more. So from this experiment, it is clear that frequency of radiation is directly proportional to kinetic energy of electrons emitted. So kinetic energy of electrons emitted by a cathode material in photoelectric emission is directly proportional to the frequency of that. So kinetic energy KE is directly proportional to frequency of radiation incident. When frequency of radiation incident on the metal surface, cathode metal surface is more, the electrons emitted will have more kinetic energy. To stop that, we have to apply a stopping potential. The negative potential applied to or retarding potential applied to the anode plate must be more. So when a frequency increases, to stop it, we have to apply more potential. Stopping potential must be more. If you draw a graph with the stopping potential along the y-axis and the frequency along the x-axis, it is saying that they are proportional to each other. So that is another graph I am going to draw here. That is this. So there is a graph. It is drawn here like this, right? This is stopping potential, and this is what is called a frequency. If a graph is drawn with the frequency along the x-axis and stopping potential along the y-axis, the graph obtained will be a straight line. That straight line goes like this. Right? This is equal to F0 because F0 is the minimum value of frequency required for uh, emission of photoelectrons. That is this much intercept is there. This intercept gives you the threshold frequency, then goes on increasing. Frequency increases, the stopping potential V0 also increases. So first V01, then V02, V03, etc. That means negative potential applied to the anode plate goes on increasing when frequency of radiation incident on the uh, cathode plate increases. When frequency of the incident radiant energy increases, kinetic energy increases. So we need more stopping potential to stop it. That means work done by the stopping potential must be more. For that, what we have to do? We have to increase the stopping potential. What is stopping potential? It is the retarding potential applied to the anode plate. Am I correct? These are the things about. And F0 is called, in this case, F0 is called threshold frequency. And this is the minimum frequency required by a radiation, so that when that radiation falls on a light sensitive metal, it can emit photoelectrons, and the corresponding wavelength of radiation is called threshold wavelength. Threshold wavelength is given by lambda 0. So this is the condition about photoelectric effect. So photoelectric effect, it is due to the photoelectric emission. Photoelectric emission means the emission of electrons, right? Electrons are emitted when radiant energy falls on it. Radiant energy is actually, what is this radiant energy is doing? Radiant energy is transferring energy. This energy is accordingly as the work function of the metal. What of the metal is depending on the nature and the nature of the surface and also the nature of the metal. Work function is measured in terms of electron volt. One electron volt is equal to 1.6 into 10 raised to minus 19 joules. This also everybody knows, right? So now we have to talk something about the laws of photoelectric emission. There are four laws related to photoelectric emission. First law, you know that. So for photoelectric emission, there must be a minimum frequency of the radiant energy, and below which photoelectric emission cannot be possible. Above which photoelectric emission can be possible. Exactly at that value, electrons are just emitted, but will not have any kinetic energy. This is first law. Next, the number of photoelectrons and hence the photoelectric current is directly proportional to the intensity of light. That is second point. And third point, the kinetic energy of the electrons emitted by a photosensitive material, what is your cathode, is directly proportional to the frequency of radiations incident on that. This is law number 3. Last, photoelectric emission is an instantaneous process. That means there is no time lapse between emission of electrons and the radiations incident on it. Just when the radiation incident and without any lapse of time, just at the same moment itself, electrons are emitted. So these are the four laws related to photoelectric emission. We will come with the next class, other part. That means Einstein's equations and all in the next class. I think you might have followed this lesson up to this much. See the video again and again and to try to understand it. Right? Thank you very much. And we will see later.